Here's an EM test board I recently made and had produced by JLCPCB, and you can see various components on this board. At the top here we have a switching regulator laid out in one certain way, and at the top right we have the same switching regulator laid out in a rather bad way. And in future videos I'd like to use this EM test board as well as these traces with various splits in the ground planes, vias and so forth, in combination with some of these near-field probes and a spectrum analyzer to see what difference it makes if we lay out a switching regulator well in comparison to what the EM signature is if we lay them out poorly, as well as how all of these traces then look if we switch them rather fast, for example with splits in the ground plane and so on. In this video, however, I'd like to first of all just focus on proper layout and routing of switching regulators, and in particular buck converters in this example.
Thank you very much to JLCPCB for sponsoring this video. These EMI test boards, which we saw at the beginning of this video and we'll see in future videos when we look at the spectrum analyzer and near-field probes, we'll be using that board. If you'd like to have a look at the schematic and design files for that board, you can go to my GitHub repository at github.com/pms67, navigate to my repositories, and there's one called EMI_testboard, which contains all of the Altium design files, as well as the firmware and STM32 IDE for the microcontroller that's on the board. There are also some project outputs, and these files, the Gerber files and the bill of materials and component placement files, you can use to actually then go to JLCPCB and order one of these for yourself if you'd like to do your own tests at home. Thank you very much also to Altium for sponsoring this video. I designed the EMI test board, and most of my designs these days I do in Altium Designer. If you'd like to give Altium a try for yourself, you can go to altium.com/YT/Phil's Lab and get a free trial. I have several videos on my YouTube channel detailing how to use Altium Designer from start to finish. I won't be going into much detail of how a buck converter or switching regulators work. There are a lot of resources online on YouTube and books and so forth. Look for buck converter. Maybe if you aren't familiar with the operation, there's loads of videos that'll help you out. I'll be giving the main tips and main guidelines for buck converter and switching converter layout in this video. Remember, these are only some overviews. If you want to go dive deeper into the topic, I can highly recommend this video by Optimum Design Associates with Scott Nance, giving a switching power supply layout seminar, and this is a great view and well worth the 50 minutes. In this video, we'll take an example of a buck converter, which is one of the simplest switching regulators and one of the most common, to be honest. Here's the topology for a buck converter, and hopefully you've seen this before or looked up some resources before you started watching this video. Essentially, this is a DC-DC switching converter. So we have a DC input source on the left here, which is typically, it could be a battery, it could be a normal power supply, whatever, as long as it's DC, and the output we take on this side across this capacitor on the output. The main elements of a switching regulator, at least this buck converter, are an input capacitor, an output capacitor, which we saw at the output. We have our main switching element, which is typically an N-channel MOSFET. We have a rectifier diode, D over here, a magnetic element, in this case an inductor, L. And this is predominantly what makes up this switching regulator. Other important parts are of course this controller, which drives the gate of this MOSFET, and typically in PWM mode. And we have this feedback network on the right, which consists of the feedback resistor 1 and feedback resistor 2. We need these feedback resistors to tap off a part of this output voltage and then feed that back to our controller so we can adjust the gate duty cycle. And by varying the gate duty cycle, the more the gate is being pushed on. So a higher duty cycle, the higher the output voltage will be relative to the input voltage. And if the gate voltage is lower on average, then of course we'll have a lower output voltage. So we have a very fast switching frequency, usually the controller. That could be 500 kilohertz, maybe 300 kilohertz, up to megahertz or 2 megahertz. So a rather fast gate switching frequency, which makes this Q, this transistor, turn off and on rather quickly indeed. If we just left this transistor to just be switching the whole time and then just use that as an output, that wouldn't be a very nice DC output. So the way we can filter that is by using this inductor and this capacitor. So we have to size the inductor and capacitor appropriately to remove or to reduce our output ripple and our high frequency switching noise. You'll also see this diode, which we mentioned earlier, and this is needed when this switch is off, and we have, when the switch Q, our transistor is off, and an inductor has stored energy. This energy has nowhere to go, there's no closed loop, and this is when this diode then becomes forward biased, and we have another loop, like so, when the switch is open. So really from this behavior, we can see that we have quite a few different current loops, and also high switching frequency loops. One loop is on the left over here, which is between the input voltage source and this input capacitor. Essentially, the main job of the input voltage source is, of course, to supply power to the rest of the system, but also feed this input capacitor. On the other side, we will have usually a load connector, so this could be a very badly drawn resistor, and this would be our load on the right side. So then we can identify another loop, which is essentially from the output capacitor through feeding the load. So by discharging the output, we can feed the load, for example. So these are two important loops, but they're not exactly high-frequency switching loops. The high-frequency loops are one when this switch Q is closed, that we are actually supplying energy from the input capacitor through the inductor, through the output capacitor and the load. So this is our high-frequency switching loop when Q is on. Now, when Q is off, so essentially the switch is open, remember we have energy running through the inductor, capacitor, and this diode. So we have this loop when the switch is open. And then we call this the rectifier loop. We need to talk about these loops because these will be incredibly important to keep small when we come to PCB layout and routing later. So we want to keep the input loop small. We want to, if we can, keep, of course, the output loop small. But most importantly, we want to keep our power switching loop, which is this one when the switch is closed, very small and very tight. And then, of course, we want to keep this rectifier loop very small as well. So these are the main principles when you're laying out a switching regulator. Overall, and very generally speaking, we can set up some layout and routing rules relating to this particular switching regulator and switching regulators in general. The first, as we spoke many times about, is to keep loops tight and small. So we want components pretty close together. We want, for example, this input capacitor very close to this switch. We want this switch node extremely tight, so the source of this transistor tight and close to the diode, as well as the inductor. Now keep in mind, a lot of ICs for buck converters will include, for example, the diode and this switching element, but a lot of them will have them externally as well. Usually it's probably preferable to go with switching controllers which don't contain the field effect transistor as well as this diode, because then you have more control in layout and routing to minimize EMI problems. So keep loops tight and small, and we'll see how to do that with a practical example. We want to start with the critical, that means high frequency and high current loops first, and these are loops 2 and 3. So when this power loop as well as this rectifier loop, 2 and 3. Once we've done our main loops, which are 1, 2, 3, and 4, we want to finish with the control circuitry. So we typically will have voltage feedback, which are these two feedback resistors, RFB1 and RFB2, and this is fairly critical. We also might have some sort of current feedback, which might be through a shunt resistor, and lastly we might have some sort of enable signals or power good signals, and we of course can do those last because they are least critical. We have some further layout and routing guidelines. An important part is that we keep all high frequency and high current components on the same side as this controller integrated circuit. We don't want to have to use vias to jump down with high current traces and high frequency because that will make field spread and cause EMI problems. We also want to make traces as short and as wide as reasonably possible. So short traces to keep loops tight, to avoid spreading energy, avoid losses and so forth, but reasonably possible because we don't want to make, for example, current carrying traces that's only supposed to carry 1 amp capable of carrying 10 amps. There's no need for that and can have negative side effects. Sensitive lines, for example, this feedback line we see from the split from this potential divider feeding back into the controller. This is a very common feedback line. We want to keep this away from areas of very high energy to avoid coupling and that we don't get any crosstalk into this very sensitive feedback trace. This in practice means we don't want to route this feedback trace, for example, very close to this magnetic element. An incredibly important part is, and these days you should probably not route on 1 or 2 layer boards unless you're very, very cost constrained, is to have a ground plane very, very closely coupled directly underneath the whole switcher. So let's go over to Altium Designer and see how we can properly lay out one of these switching regulators. Here I'm looking at the schematic for the EMI test board, and I have duplicate switching regulators, one which I laid out well and one which I laid out poorly. We're just going to be focused on how to lay out a switching regulator properly. Here's the switching regulator IC. This is a pretty random switching regulator IC. It's very simple because it already contains the switching element, which is the transistor, as well as the diode. We have an input pin, pin 5, which we need to bypass with this large capacitor, 22 microfarads, which is C3. We have an enable signal, which I've typically poured low, but I can pull high to the input voltage with this solder jumper. We have a switch node output. Remember, this was a very critical output and one we need to keep tight, which feeds the magnetic element L1 and an array of output capacitors C5 and C6. We also have this feedback network where we take the output voltage, divide it down and feed it back into this FB pin. And remember, this is a fairly sensitive signal and pin. We also have this bootstrap capacitor, which aids with efficiency. We won't go into detail with that, but we'll include that, of course, in our layout. We won't lay out any of the rest of the board, so I'll just take these components and guide you through how I would go about laying out a switching regulator. So let's jump to the PCB document in Altium Designer. You can see all of my components I've imported over here, but I've already singled out all the components we just need for this one switching regulator. The EMI test board is a 4-layer board, but for the sake of simplicity, we'll just make this into a 2-layer board. So we have a top layer. If you look at the bottom, this is the red, everything with red traces. And then we have the bottom layer, which is everything with that is blue. If I double click, I'll rename this to L1 SIG, and I'll name the bottom to L2 ground. This is just for me to see, okay, I've got one signal layer and one ground layer, which I try not to use for any signals. So let me start off before I do any ground pulls or anything on the bottom layer. Let's just see what kind of area this switching regulator will take up. I can press G to change my grid, and I'll just do a rough placement. Let's put it on 0.25 millimeters. And U1 was our main switching regulator RC, and I'll put that somewhere in the middle, and this is where I'll start with. I'll hide some layers to make it more easily visible, and then I'll also hide this component designator. So the layout of the IC is that we have our ground pin at pin 2, we have our input voltage at pin 5, which happens to be 5 volts, our switch node is at pin 6, enable signal is 4, feedback node is 3, and we have this boost pin, which connects to our boost capacitor in pin 1. So remember, we want to keep our loops fairly tight. So the first thing I would typically do is see how closely I can place my input capacitor. Input capacitor was C3, so I can move that over here. If I hold the component, press space to rotate, I want it, not close like so, because this will be very hard to manufacture, and also it's too close to these other pins. But let me just put it in the vicinity first, so something like this. I could have placed it like this, but then you can see my loop between this ground and this ground is slightly larger. So I'm placing it like so, because I have immediately a very short trace between my input 5-volt pin and this bypass capacitor, as well as my ground area or ground loop is already shorter. Let me hide my designator. Now you could think, okay, maybe I can put it like this, but why wouldn't I put it like this? Because then my buck 1 switch node and this capacitor will get in the way, because I typically want to place my inductor here. So as a first guess, this seems fairly alright for this input capacitor. Next, let me do my switch node. Remember, this is the node we want to keep rather tight. This was this node over here. We've just done our input capacitor close to the IC's input, and now let's look at this switch node. So the switch node, in our case, we're lucky. Well, lucky because our layout job is slightly easier because we don't have to worry about a switching element or a diode. So I'll take this inductor, get rid of the designator, and you can see I have got 2 parts of this inductor. One is from the switch node and one connects to the decoupling capacitor outputs. Now, we have 2 options. Well, we have multiple options, but one option would be to place the inductor somewhere like this. This means we have buck switch goes pretty much straight up into this inductor, but then the output of this inductor, which then feeds into these 2 decoupling capacitors, would have to be placed, for example, somewhere like this. This isn't ideal because our ground pin of this switching regulator is somewhere over here. So ideally, we want to flip this 180 degrees and kind of put it somewhat midway of this converter IC. This way we have a fairly short path to buck switch, and our buck output, these capacitors here, if I just get rid of the designators, I can put, somewhere like so as a very initial rough placement. In this way, I've tried to keep my loop small from buck 1 switch to this inductor, as well as the output side of this inductor back to these 2 capacitors, for example. We have to keep in mind, though, that we also have this buck 1 boost node as well. So we can't forget our C4, which was this 100 nanofarad capacitor. If we go back to the schematic, this was this capacitor, C4. So that has to still go in the way, so we might have to extend this a tiny bit, move this inductor up. Let me just rotate it like so, get rid of the designator. And in this case, ideally I want to put it somewhere like this, but the silkscreen is in the way. The way I can move that, because of course I want to prioritize component placement rather than silkscreen, I go on to U1, unlock primitives, and then I can go to my top overlay, and then I can actually move this about and change the position, like so. This is just to indicate what is pin 1, so I'll just move it over here, click on U1 again, and lock primitives. In this way, I can then move my inductor down quite a bit, so I have a nice, fairly tight loop. I can move this over just a bit more because, we don't want to route buck 1 switch out to the right very much, we just want to go up, shortest path possible. Let me press 3, which goes into a 3D view, and this is good to check, because we will have to have this board assembled at some point, at least we want to. So we want to make sure that these components are, touching like so. This would be probably almost impossible to assemble. So that's why we want to keep these still spaced out a bit so it's manufacturable. The nice thing now is we can move in these switching regulator output capacitors to keep these loop areas very tight. So the output of the inductor will feed these 2 capacitors, and the ground pin is then very close to the output ground pins of these output capacitors. Remember, we are now looking at this kind of output or switching loop over here with a switch node to keep very tight. So now we've done a very, very rough placement of the input capacitor, output capacitor, magnetic element, as well as this boost capacitor. We still have these three resistors here. R1 was our enable signal, along with the jumper. And remember, we can do this last because it's DC, it's very low energy. Not entirely critical at all how we route this. What is critical, however, are R2 and R3. R2 and R3 are these feedback resistors over here. So we tap off from the output, we divide it down and feed it into pin 3 of our IC. Then we get rid of these component designators, and our feedback pin is down here. So later when we come to routing, we want to go out from the switch node into our magnetic element along with these capacitors, filter, remove high frequency energy, and from the output of our last decoupling capacitor, we want to route a trace away from this magnetic element into our resistor dividers. So we can place our resistor dividers. So one possible way of arranging these resistor dividers is because we are thinking, okay, we might want to have some sort of trace come out like so into this resistor divider, and then we can route, for example, into this feedback pin like so. This way, we keep this sensitive trace away from this magnetic element. That's pretty decent. In multi-layer designs, if we don't have a two-layer board, I would typically use a via to dig down into an internal layer on the other side of the board, route on the other side of the board far away from any high energy, high frequency circuitry, and then route back up here with a via and go back into this feedback network. But for a two-layer board, something like this seems pretty much fine. So as a first initial guess and a very simple layout, this is already a pretty good start. Of course, you can do refinements, but as a first initial pass of a layout, this is something good, right? We kept our buck switch node rather small, our output and input loop small. We were thinking of our ground placement and so on. We have still our enable pin with our enable signal, and we do that last. Then we get rid of the designators again. And this is not critical at all, right? I could place this resistor somewhere over here and route some dodgy line down there. That would be fine. But for the sake of neatness, we might as well do it somewhat properly. For example, just having this resistor here, and then this solder jumper, because we want to actually manually solder something on. If we want to enable or disable this regulator, we would then, put somewhere else and just route a line into this buck enable pin. So I'll just move this out of the way for now. If we go into 3D view, we can see this is pretty decent. We've got a pretty tight layout. We could move things in closer, try and optimize these nodes. But for the layout of this IC, this seems pretty decent to start with. So the first thing, of course, you would have a dedicated ground plane, usually multi-layer boards or multiple dedicated ground planes. On a two-layer board, our bottom layer would be ground. I'm going to place a polygon, so if I press P on my keyboard and then press G, I can start placing a polygon. I'll press G to change my grid, and let me just make a large ground plane underneath and extending out well past any of these components. And this is fairly arbitrary, don't worry. Normally you would make this the size of your PCB. But just for illustrative purposes, I'm going to put a ground plane underneath. Let me just call it GND, change the net name, and then click Repo. So if you look at the PCB, on the bottom side we have this ground plane, and remember this is just an example. You would want to make this ground plane a lot larger and the size of your PCB. In this way we can now hide the bottom layer if we right click and click hide, and now we can do the routing of this. You can either use polygon pores to connect this up, and this is what I would usually do. Press P and then G, for example, the output node here. I would use a 0.25 millimeter grid, for example, and just draw a minimum size which can carry the current you want, if this is 1 amp, 2 amps, or even less, and then give it the net name. And you can see Altium has already done thermal relieves. This depends on your copper balance. Usually I do no thermal relieves, especially I have very small copper planes like this, and I haven't had problems with solderability or manufacturability. The way I would do that in Altium Designer is go to Design, Rules, Polygon Connect, and then just do Direct Connect. This is very simple. Of course, you should set up more complicated rules, but for this will do. Click Repo, and you can see we have a solid connect. Now remember, these planes, or these, if you use traces instead, should only be as thick as needed, or as wide as needed rather, to carry the current you want. You don't want to make these arbitrarily large, and this is especially for the switch node. For the output node, this is probably still okay, but remember that large copper pores are coupled with a ground plane underneath, and for multi-layer boards, this will be very closely coupled underneath. This will increase the capacitance. And the switch node, we don't want any capacitance. But for the output node, this is fine. So for the switch node, we can do something similar. So for the switch node, done something fairly similar. Try to keep it as small as possible that we just cover the pads. We have a wide enough trace to carry the current. And that's about it. On the other side, you could either do again, on the side of this boost output, we can either use a very wide trace, but if you're worried about copper imbalance, you can also add a thermal relief to this buck1 switch node over here. The way we can do that, for example, is by clicking on the pad of this capacitor itself, is clicking on the capacitor, unlocking primitives, and then clicking on this first pad, scrolling down and adding a thermal relief like so. And then we can change the thermal relief properties by clicking on these 3 dots, change it to relief connect, and then choose suitable air gap, and conductor widths. Then if we re-pull this polygon, you can see I've added thermal relief. And this might be useful if you want to, really make sure that you don't have any copper imbalances and you don't want to get tombstoning on your small SMD parts. But remember, we don't want to make this switch node polygon too large, and it's perfectly fine to use traces as well. For this 5 volts, I'll just use a very wide trace. Something like 0.6 millimeters is perfectly adequate, and as you can see, this is a very short connection, so really nice. Then, of course, we have all of our ground connections. So if you're just doing a single layer board or a 2-layer board where the ground plane is very far away, I know in this example this looks like a 2-layer board, but typically I would lay this out with at least 4 layers, so very closely coupled ground plane directly beneath all of this circuitry. Then it doesn't really make sense to add, a power pole connecting all these grounds up. It's perfectly fine just to have vias for every one of these components and link them up with traces. So I can press P and V to place vias. I'm just using the standard vias, 0.6, 0.3 millimeters, and of course you want several of them to make sure you can handle the currents. So you can see my via placement, I have several ground vias, and you can either hook them up with polygon poles or with traces, typically at least 1 via per pad. And you don't want to have your vias, for example, in the pad like so. You don't want them terribly close either. Some distance like this seems perfectly adequate. If your vias are too close and they're not tented, then you can have problems with soldering as well. For the switch IC, I might place 2 vias right next to this ground pad and a couple of vias at the input capacitor as well. And these will then all tie directly down to the ground plane. You can also see I've just used a simple ground connection for this feedback divider network. You don't have to do any special routing for that if you have a solid closely coupled ground plane underneath. So an example could be, remember the ground pole isn't entirely necessarily here, but for me it looks more aesthetic than traces in this example. Solderability should be fine because I have a fairly large copper pole over here, a large copper over here, and I've never had any problems with solderability of then these ICs with, it's not a large copper pole anyway. Here I've just added a thermal relief just in case because we have thin traces coming out of the buck on this side of these pads. When I just have, for example, this single enable pad, single enable resistor with a ground pad, I will just use a fairly wide trace coming out to via, and remember the via not in too close. In a 3D view, this would then look something like this, something pretty reasonable. And the intercapacitor has its own set of ground vias as well. So remember the order of things we did. We did the layout really tight. We did the buck switching node routing, output node routing, input, and so forth. And lastly, we can focus on critical traces, for example, this buck1 feedback trace. As before, if you have a multi-layer board, I would go out from this pad of the output capacitor via internal trace or other side of the board to make sure this is, far away from any high energy signals or high energy areas. But in this case, I'll just use a fairly thin trace, 0.25 millimeters is fine. Route that out far away from the magnetic element and directly into this first resistor. Then I can route the other side into this feedback network over here. And there we go, that's it. So remember, thin traces, this is a fairly sensitive high impedance input pin, this feedback pin, and away from the magnetic element. What you don't want to do is, for example, take it directly from the output of the inductor, route it around the inductor, close to the ICs, like so. This is not what you want to do, right? I've used a fairly short path from the output capacitor away from the magnetic element into this resistor. That's it. And the last trace, we just have this very simple buck enable signal, and we just feed that in. And whatever that then connects to, can be as long as you need it to be. And there we go. So 3D view, remember, this is just an example. The ground plane underneath should be much closer, directly underneath the layer you're routing this on. We have all of the components on one single side. We've kept our nodes short. We've used just enough width on the copper traces and planes to support the currents we need. Nodes are kept tight and short. This feedback trace here is routed from the output capacitor further away from this IC and this magnetic element as to avoid any coupling into this feedback divider network. And that's a very brief way and a very simple way of efficiently laying out switching regulators. So thank you very much for watching this video. I hope you learned something, and I hope you can follow the links which I'll leave in the description to more detailed switching regulator layout and design by Altium Design Associates. We'll be seeing this board, this EM test board, in future videos to see, what differences make laying out a regulator fairly neatly compared to laying it out not very well. And also, if we route traces over splits, what effects does that have for electromagnetic interference? If you haven't already, please do subscribe and please do leave a comment and a like if you liked the video. Thank you, and I'll see you next time.